All right, welcome to lecture 21. And lecture 21, like most of them, I broke it up into three parts. So there's parts A, B, and C. So all of these parts, we're going to talk about how atoms get together to make compounds. So you've already heard a little bit about compounds, right? Like we talked about how to name compounds, and we talked about how there's different kinds of compounds, ionic and molecular and acids. So in this section, what we're really going to get into is why is it atoms join together to make compounds? And how does that happen exactly? So really in this lecture, we're going to focus on how atoms get together in ionic compounds. And the other two sections, we're going to look at what goes on in molecular compounds, so in parts B and C. All right, with that, let's go ahead and get started. Okay, so before we get into compounds, I got to remind you of something about we talked about in the previous lecture, which is this idea of valence electrons. So valence electrons, just to remind you, valence electrons are the electrons, oop, I'm writing the wrong word there, excuse me, the electrons in an atom's outermost shell, an atom's outermost shell. Now, the reason why we got to focus in on these electrons is because they're the ones used in bonding to other atoms, used in bondings to other atoms. So let me just remind you, one way you can know the valence electrons, you write out the electron configuration. When you write out the electron configuration, you look for the highest numbered shell, and you figure out how many electrons are in that shell. Now, sometimes that shell, remember the shell's the big number, that shell might be divided up into two parts, so you'd have to add them together. So for example, for sulfur, the outermost shell is the third shell, and in the S part, there's 2 electrons, and the P part, there's 4, I should say. That adds up to a total of 6 valence electrons. If we look at lithium, the outermost shell in lithium is the second shell. There's only electrons in the S part of it. There's only 1 electron. All right. Now, I also mentioned to you, I think last time, that the easiest way really to figure out valence electrons, because we're going to be talking about valence electrons this whole unit here, is actually not to write out the electron configuration. It's just to glance at your periodic table. So when you look at your periodic table and you look at the column number, that is telling you how many valence electrons an atom has. So for example, in sulfur, the outermost shell again is the third shell, and there's a total of 6 electrons in that third shell. Or if I asked you about lithium, in lithium, the outermost shell is the second shell, and in the second shell, there's 1 valence electron. So the column number tells you the number of valence electrons. If I asked you about boron, he's got 3 valence electrons. If I asked you about, I don't know, silicon, he's got 4 valence electrons. So if you look at those column numbers, that'll tell you the valence electrons. This only works for the A columns, not the B columns. We're not going to deal with the B column, so so I wouldn't get too hung up on that. All right, with that, let's just double check this is making sense. How many valence electrons are in an atom? You can tell by where it is on the periodic table. Okay, before we get into compounds, let me remind you a little bit more about valence electrons. And one thing we haven't talked about yet is often when we want to talk about valence electrons, the way we represent them, they're often represented by dots. So a dot is sometimes a symbol for an electron. So you see a few examples of this right here. And you see like lithium has 1 dot on it. Why does it have 1 dot? Because it has 1 valence electron. It's in column 1A. Why does carbon have 4 dots on it? Because it's in column 4A. So it has 4 valence electrons. Or why does fluorine have 7 dots on it, I should say, if you count them up, because it's in column 7A. All right, so these dots are a way of representing valence electrons. Now, if you're wondering, like, how did they decide where to put them, and why are they on the left and all that? Well, let me go over that. All right, so the way you're going to know how many electrons, how many dots you got, how many valence electrons you got, is you look at the column number, right? So you look at the column number. That'll tell you how many dots. As far as where they go, let's do a little example of that. So if we have some element X, and I want to talk about its valence electrons, I'd write the symbol, and then I would put in enough dots to represent all the valence electrons. Now, where you put in the first electron, if it only has one, it doesn't really matter. You could put it on the left side, the right side, top side, bottom side, it doesn't really matter. So if it has one electron, you just put 1 dot. Now, if it's got 2 electrons, the second dot should not be right next to it. The second dot really needs to be on another side. What side? It doesn't really matter. Just on a separate side. Why is this? There is some reasoning behind this. There's a theory about how electrons want to spread out. So kind of to show that, we're putting them on different sides. Why are they spreading out? Well, one way to think about that is they all have negative charges, right? So they're going to want to spread out. So if there's a second electron, it should be on another side of the symbol. You can see that sort of in beryllium. If there's a third valence electron, you would put it on yet another side. 4, you go to the last side. That's kind of what we saw in carbon, right? And then if you've got 5 electrons, then you're going to have to start doubling up. 5, 6, 7, 8. The most you could ever have is 8. Atoms don't typically have more than 8 valence electrons. All right, so you spread them out the most you can, and then if you need to, if there's more, you double them up. Okay, all right, so with that, well, how does this relate to compounds? Well, it turns out the way that this relates to compounds is that atoms are happiest. Atoms are, we'll say, most stable when they have 8 valence electrons. 8 valence electrons. So atoms, really, they would love to have 8 valence electrons. Now, it turns out there's one column on the periodic table where the atoms already have 8 valence electrons. And those are going to be very stable atoms. They're not going to react. They're not going to do crazy things. They're not going to blow up. In fact, they won't even typically join up with other atoms. So the atoms on the periodic table who have 8 valence electrons, what would we call that column? Which column has 8 valence electrons? Okay, so the column is going to be this column, right? Column 8A. And those, again, were called the noble gases. The noble gases. Now, it turns out every other atom on the periodic table, they don't have 8 valence electrons normally. So these fellas only have 1, right? And these fellas only have 4, right? So every other column on the periodic table doesn't have 8 normally. So what they're going to do is they're going to try to get together with other atoms to end up with 8. So maybe we should write that down. So atoms are most stable when they have 8 valence electrons. If they don't have 8 valence electrons, so I'm talking about everybody except for the noble gases, they will join with other other atoms to get 8. All right. So the reason why atoms get together with other atoms, the reason we end up with compounds really, is because atoms have this need to end up with 8 valence electrons. Now, one other way I'll say it, you can either end up with 8 valence electrons, or you can end up with 0 valence electrons. That would be another way to become a happy atom. So what does this mean? It means that noble gases, they're already born with 8. They're not going to get together with other atoms. They're typically not found in compounds. Every other atom on the periodic table, they're miserable. I want 8. I don't normally have 8. So I'm going to join up with somebody else to get to 8. And that's what a compound really involves. Atoms joining together to get that magic number of electrons, which is 8, or you might think of it as 0. 0 would also work. All right, so let's talk about exactly how is that going to work? How can they end up with 8 valence electrons? All right, so let me flip over to another slide here. All right, so let's talk about what happens in an ionic bond, ionic bonding. So ionic bonding involves the transfer of electrons between two atoms. Now, why are electrons going to get transferred? Because both atoms want to end up with 8 valence electrons, or you could kind of think 0 is another option. All right, so let me show you a little example. All right, how can two atoms get together and end up with 8 valence electrons? So the example I'm going to show you, I'm going to talk about what happens when you have sodium and chlorine, all right? Sodium chloride. So let's talk about what happens when salt forms. So NaCl. So let's start off, we're going to talk about the atoms individually, and then we're going to look at how and why they get together. So some of this I'm going to go through a little fast because it's things we've heard about before. So sodium, let's start off with sodium. Sodium is Na, and if I ask you how many protons it has, it's 11. So it's got 11 protons. And if I ask you in a sodium atom how many electrons there are, there's 11. All right. Now, for sodium, while we're at it, to help us understand what's going on, I'm going to write out the electron configuration. So, you know, the 1s2 business. 1s2, 2s2, 2p6, 3s1. That's what it would be. And one last thing I want to tell you, if I ask you how many valence electrons sodium has, it has 1, right? You can tell that by the column number, or you got to look at what I just wrote out. Third shell, and the third shell, there's 1 electron. It has 1 valence electron. All right, now let's imagine it next to a chlorine. So chlorine is got its element 17, so let's kind of do the same thing for chlorine. Chlorine would have 17 protons, and a chlorine atom would have 17 electrons. So when we want to think about where those 17 electrons are, we could write out the electron configuration. Oop, that's wrote there. Erase that and fix it. All right, that would be what it is. So 1s2, 2s2, 2p6, 3s2, 3p5. And if I asked you how many valence electrons it has, the third shell is the outermost shell. And in the third shell, the number of valence electrons, 2 and 5, it adds up to 7. All right, yeah, that's right. It's in column 7A, so that sounds right. Okay, so both of these atoms normally, if they are in the universe, they're not going to be happy atoms. Oh, so sad. They both want 8 valence electrons, and neither one of them has 8 valence electrons right now. So if these two atoms were to be near each other, though, they can make a little deal. And the deal they're going to make is the sodium can agree, hey, you know what? I'm going to give you one of my electrons, Mr. Chlorine. So it'll give up an electron to the chlorine. So when this happens, when there's this transfer of electrons from one atom to another, let's talk about what we're going to make. Well, sodium, after this transfer, it gives away an electron. Sodium would still have 11 protons, but now it would only have 10 electrons. It gave one away, didn't it? Now, chlorine would still have her 17 protons, but she got one extra, so now she has 18 electrons. So one thing that's going to be true about these guys is they're going to have charges now. The sodium would have an extra positive. So this guy would have a +1 charge. The chlorine has an extra electron. It would have a -1 charge. Now, the other thing that's true about them, if we have these charges, opposite charges stick to each other. So opposite charges are going to want to stick together. Opposite charges are attracted. So after there's this transfer, we end up with charged particles that want to stay together. And that's what's going on in salt. So in salt, you have a bunch of positive and negative charges that stick to each other, specifically the sodium and the chloride. Now, why would there want to be this transfer? Why does this even happen? Well, again, the reason why it happens, if we look at how the electrons are configured, let's see what happens after this transfer. So after this transfer, Mr. Sodium gave up its electron. It only has 10 now, right? So where are they? 1s2, 2s2, 2p6. So there's two ways of thinking about it. Either you could think the third shell is now empty. That would be one way of thinking about it. The other way you could think about it is the outermost shell is the second shell, and it has 8 electrons in it. So either way, you get the same answer. 8 valence electrons or 0 is a good amount. Nature likes 8 or 0. All right, so what about the chlorine? The chlorine, now if we talk about what he has, remember he got that extra, so he took one from sodium, so he doesn't have 17 electrons anymore. Now he's got 18. Where are those 18? Let's write them out. 1s2, 2s2, 2p6. Oh, I'm going to run out of room here. Let's finish it down here. 3s2, 3p6. The outermost shell now is still the third shell, isn't it? But in the third shell, with that extra electron, instead of having 7, let's count them up. Now he's got 8. 2 and 6 makes 8. So by grabbing an electron from sodium, he now has 8, the chlorine. And the sodium actually is in good shape too because he got rid of an electron. So when he got rid of an electron, that made him only have, he has 0 now, right? He only had 1 to start with, so he gives it away. Now he has 0. The result of this is we end up with charged particles that stay together. And that's what goes on in ionic bonding. Ionic bonding is when two atoms transfer their electrons, we get these charged particles, and then after they become charged, they actually stick to each other. All right, so there's lots of ways to represent what happened. One way to represent this is, let me erase a little bit here. And let me show you, I kind of went into a lot of detail here. Typically, we probably won't need to get into quite this much detail, but I wanted you to understand what's going on. Typically, the way we're going to show what's going on is we're just going to use those dots to represent the electrons. So let's talk about one last way to represent what happens when sodium and chloride bond. All right, we start off with, instead of drawing all the electrons out, let's just use dots, and I'm going to use dots to represent the valence electrons. We start off with a sodium with 1 dot, 1 valence electron. We start off with chlorine with 7 valence electrons. Let me erase this so you don't get confused. With 7 valence electrons. Okay? Now, what's going to happen, you put them near each other, this electron is going to go over to the chlorine, and after we're done, what do we end up with? The sodium has no electrons left, and the chlorine now has got that extra. Now the chlorine has 8. Okay, so if we want to understand how this bonding is going on, this would be one way of showing it. Now again, after there's this transfer, we end up with charges. Sodium got rid of an electron, positive. Chlorine gained an electron, negative. All right, now, and I want to check my notes for one thing here. Give me a second, because I want to see how your book does this. Yeah, when you see this in your book or in Sapling, the other thing you might notice, for the fellow with all the electrons, often we're going to put them in a bracket. to kind of keep them all together. So that would be one way of representing what happens in this ionic bond forming. Okay. All right. May not quite make sense yet. Let's talk about another example. Let's do another example. All right. Let me flip over and we'll do one more here. All right. Let's do another example. So we're trying to understand what happens in an ionic bond. All right. And this question it says represent, using dot symbols, represent the formation of an ionic bond between a magnesium and an oxygen. So let's draw them out. Let's draw what does a magnesium atom look like normally. And again, I'm just going to think about the valence electrons, and I'm going to use dots to represent them. So magnesium has 2 valence electrons. Going to give them 2 dots. And I'm thinking about him getting together with an oxygen atom. Oxygen has 6 valence electrons, 6 dots. Let's put them in. 1, 2, 3, 4, 5, 6. All right, so if we put these 2 atoms near each other, they're going to transfer electrons. Magnesium has 2 to give away. And if you look, there are 2 spots for oxygen to take them. He's got 6. I'm trying to put up 6 fingers. He's got 6. And he can take 2 more to get to 8. So that's exactly what magnesium's going to do. He's going to give those electrons to oxygen. All right, so I'm going to represent what happens after this transfer. Magnesium would end up with none. He gives 2 away. And oxygen is going to take those 2. So he's got the 6 he started with, and he's going to grab those 2 from magnesium. I'll use blue to represent the ones from magnesium. And now with those extra 2, he has 8. Now, if I wanted to show you what is going on a little bit better, again, now we end up with things with a charge. Mr. Magnesium loses 2 electrons, so he's going to be +2. Oxygen has gained 2 electrons, so he's going to be -2. And often the negative guy, we put a little bracket around. All right, so with that shows you a bond between magnesium and oxygen. And again, this should sort of help you understand. Remember a long time ago I said, magnesium, he's going to make a +2 ion. Well, this is sort of the reasoning, right? He's got 2 valence electrons, and he tends to give those 2 away. That's why he made a +2 ion. Or oxygen. I said, oh, oxygen, anybody in this row, they made a -2 ion. Well, why? Because they got 6 electrons, that means they have room to take 2 more from somebody. And if they take those 2, they'll end up with a -2 charge. So this kind of goes along with the always and forever charges that we learned. It kind of goes along with that. All right, let's do one final example. One final example of this. All right, one final example of trying to understand ionic bonding. All right, so our last example. Let's pretend we got a calcium in the world, and it's going to join up with the chloride. So calcium and chloride getting together. So first thing I want to do is draw how many electrons, valence electrons, these atoms normally have. So let's start off with calcium. Find on your periodic table, how many valence electrons does calcium have? Okay, so it should be 2, right? And I'm going to write, if I represent it, 2 dots. All right, that's calcium. All right. Look at your periodic table. Tell me how many valence electrons does chlorine have? Okay, it should be 7. All right. So we'll draw them up here, and we'll put 7 dots. Is that 7? Yeah, I think that's 7, right? Now, let's imagine these 2 things get together. Now, there's something you might notice, right? Calcium has 2 electrons that he's trying to lose. All right? Now, but look at the chlorine. How many empty spaces does he have? He only has room, because he already has 7, right? He's only got room for 1 more. So he can't take both of them. Calcium is trying to give away 2, but chlorine only has room for 1 of them. So what's going to have to happen in this case is the chlorine doesn't have room for both of them. So calcium is going to actually need to find 2 chlorines to give its electrons to. So another chlorine would have 7. That means he's got room for one more. So calcium can give 1 electron, oh, well, that's going to be a little messy, to this guy, get him to 8. Calcium can give his other electron to this guy and get him to 8. So what is going to really happen in this case is calcium is going to end up joining up with 2 chlorides. Wait a minute. Remember back in the day when we were running formulas and I said calcium, it's going to join, it has a +2 charge and chloride's -1. So the right formula when you put them together, oh, it's going to be CaCl2. Well, this is sort of why that's happening. Why is it that you need 2 chlorines? Because you need 2 spots for calcium's electrons to go. All right. So let's talk about what is that going to look like if we write out what we make here. All right. So to represent what happens in this, calcium gives away both its electrons. If I wanted to show you what it turns into, I would say it turns into a Ca+2. Chloride has room to take 1 more electron. It'll get to 8. Now, maybe I'll use its new electron, the one I got from calcium. Maybe I'll do that with a red dot. That's the extra electron it grabbed from calcium. But actually, you're going to have 2 chlorides, aren't you? Because you need room for both of those electrons. Like that. Okay. So again, this would be a representation. Ah, there we go. A representation of how these atoms are getting together. Oh, and the chloride would be -1, wouldn't it? I guess we'd write that outside the bracket. Okay, so that would be one way of showing how these electrons have moved around to form an ionic compound. All right, with that, hopefully this is making sense. If not, you can ask me some questions. We'll practice it during our Zoom time, and then we'll have some homework on this, I suppose, too. All right, so if you have any questions, then let me know. Otherwise, that's it for ionic compounds. We're going to move on to what goes on in molecular compounds in part B of this lecture.